Very good morning. We are continuing multivariate linear regression. Today we discuss sampling distribution of parameter estimates. We will see expected value of beta cap, covariance of beta cap, and confidence interval for model parameters with an example. Let us see what is there in the next slide. I am sure you are enjoying the lectures.
Next is you have to have sampling distribution of beta. Sampling distribution of beta cap. Getting me? So similarly, in MLR also we have found out the sampling distribution of beta cap. Okay, so here what is required to be known, if you want to go for that sampling distribution of beta cap, then you must know what is the expected value of beta cap, and you also required to know what is the covariance value of beta cap. These two we require to estimate. Okay. So now let us see that what is the expected value of beta cap. Expected value of beta cap, we can write that expected value of x transpose x inverse x transpose y, because beta cap formula is this. So x is fixed here. So we can take x transpose x inverse x transpose out of the expectation. It will be expected value of y. Now all of you know what is the expected value of y. See, expected value of y, suppose y is x beta plus epsilon. So if I say that what is the expected value of y, then expected value of x beta plus expected value of epsilon, this is 0. So this one is x, expected value of beta, beta is constant, so it is x beta. So I will put here x transpose x inverse x transpose x beta. Again you see x transpose x inverse is, and particularly x transpose x is a symmetric square matrix, and its property, this transpose into this will be an identity matrix. So I beta, so we can write this is beta. So unbiased ST method. Okay. What you require now? You require covariance of beta, covariance of beta cap. So this can be written like this: expected value of beta cap minus expected value of beta cap. Can we write like this? This into beta cap minus expected value of beta cap, this transpose. We have seen earlier this one. Now what is beta cap minus expected value of beta cap? Expected value of beta cap is beta. So this can be written like this: beta cap minus beta. So beta cap is x transpose x inverse x transpose y minus beta. Yes. So then you put here x transpose x inverse x transpose y is x beta plus epsilon minus beta. The resultant quantity will become x transpose x inverse x transpose x beta plus x transpose x inverse x transpose epsilon minus beta. And this quantity is I, so this is beta. So, beta minus beta cancel out that one. So, ultimately you are getting x transpose x inverse x transpose epsilon. So, your beta cap minus capital beta is this. Then our covariance, then what will be the second one? Beta cap minus beta transpose. So, this one you can write x transpose x inverse x transpose epsilon transpose. So, this will be just, it will reverse way epsilon transpose, then this x will come now x, then x transpose x inverse is x in transpose inverse, that remains same because of symmetric matrix. So, this is the quantity now. What is our covariance of beta cap? That means expected value of beta cap minus beta cap minus beta transpose, that was the formula. So, I will write this here, our beta cap minus beta is x transpose x inverse x transpose epsilon, and the transpose of it epsilon transpose x x transpose x inverse. Okay. So, as usual we will bring the x factor out of the expectation operator, then we will get x transpose x inverse x transpose expected value of epsilon transpose x transpose x inverse. Okay. This fixed value does not require the expectation operator here. Now, question is, what is epsilon transpose? Getting me? Now, if you see the equation y is n cross q equal to x beta plus epsilon, where epsilon is also n cross q. Now, then epsilon transpose, this will become, this is n cross q and this one will become q cross n, then the resultant will become n cross n. Getting me? Resultant will become n cross n. So, if you can remember the one of the assumption what I have told you in the last class of multivariate regression, that I said that across this x, the different across x observations, when you see the y value, ultimately we say that covariance structure, the same covariance structure, this covariance structure with respect to what? With respect to the y, there are qy variables. So, ultimately what will happen then, this quantity will become like this. This one is x transpose x inverse x, then this one will become into I, that there is one operator called Kronecker, this quantity will become like this. So, this symbol is known as Kronecker product. Kronecker product. So, into x transpose x inverse, this will be the case. Now, why this here n cross n, then ultimately what will happen? For every dependent variable, for y1 n cross n, for y2 again n cross n, for y3 n cross n, yq n cross n. So that is why again what will happen ultimately, if you go by the multiple regression mode, there you will find out that for every, here if it is one y variable only, it sigma, this will not be sigma, then it will be sigma square, then it will be sigma square, it will be sigma square. Now when we create the covariance matrix of epsilon for multiple regression also, we get n cross n, but here everywhere when the diagonal element will be sigma square, because for every element of that error, that the variance is sigma square, and off diagonal definitely will become 0. So here in this case what is happening? In this case it is happening like this. Suppose I have y1, y2, so similarly yq, this side also y1, y2 like yq. So see what is happening here. Here you are getting y1 versus y1, this case also you will be getting, what is this? This is, you will be getting here sigma, and here also you will be getting sigma, here also you will be getting sigma, here also you will be getting sigma. Okay, so that is why this total, this arrow term, this Kronecker alpha is coming because of Kronecker product is coming because of this. So you will get this type of terminal, this type of relationship, which will be, if you further simplify, x transpose x inverse, x transpose x, x transpose x inverse, then this Kronecker product, this. Okay, now x transpose x inverse, x transpose x is I, so ultimately that will not be there. So x transpose x inverse this. But there will be this Kronecker product. Why this? For every y, x transpose x will be multiplied to every y. Here this one will be x transpose x inverse, here it will be mine x transpose x inverse. Okay, here it will be x transpose x inverse, everywhere it will be multiplied. Okay, and ultimately what we want to say that ultimately that for this one, now you think of the situation like this. Suppose here we are talking about individual y vis-a-vis x, then if we go by the y expected y value, therefore every observation what will happen? Every observation that sigma value will be equal. Every observation of x, the y sigma will be equal, and that is true for all other y values also. So as a result this is fine, but when you will be using for a individual y like y1, like y2, like your yq, so you have to be very judicious that what you will be using. So you will be using sigma, I think I have given you earlier also, sigma is sigma 1 square, sigma 1 2, sigma 1 3, like this sigma 1 q, then sigma 1 2, sigma 2 square, sigma 2 3, like sigma 2 q, and this manner sigma 1 q, sigma 2 q, like this sigma q q means sigma q square, somewhere there will be sigma k square for the kth term. Okay. So if I go by individual y variable for the kth variable, this diagonal element you take kth variable, here I think you can still remember that we used in univariate case x transpose x and sigma square, so that means sigma 1 square, x transpose x inverse sigma 2 square. So like this x transpose x inverse sigma q square. When you talk about individual dependent variable part. Okay. Now that means I must know that sigma 1 sigma k square k equal to 1 to q. If you know this, then you know the variability part, that covariance of beta k. Getting me? What I mean to say, that if I consider yk variable, that case the covariance of beta k, we are saying that it will be x transpose x inverse sigma k square, that we are saying. That is what we have seen earlier also. Okay. So, but question is that sigma is not known, capital sigma is not known. So, how do we understand that what is this sigma? But you know this epsilon cap is known to you. Now, if I make epsilon cap transpose epsilon cap, then what is this value? This value epsilon transpose will be q cross n, and epsilon will be n cross q. So, this quantity will be q cross q. Okay. So, this is what is your SSCP error part. Instead of in MLR you have written this one epsilon transpose epsilon, when you have done you said SSE, and this you say SSE, and it was a scalar quantity. But here this is q cross q matrix, that is why it is a vector quantity. Getting me? And this value, so SSCPE, this value is n minus p minus 1 into capital sigma. Getting me? Now what we will do, if we write like this, SSCPE, if I write S11 or S1 square, let it be right, S1 square, S12, S1q, because this is q cross q, then S12, S2 square, S2q. So, like this if you write S1q, S2q, SQ square. So, this is n minus p minus 1 into sigma 1 square, that cap, then sigma 1 2 cap. So, like this sigma 1 q cap, sigma 1 2 cap, sigma 2 cap square, sigma 1 2 2 2 2 q cap. So, like this sigma 1 q cap, sigma 2 q cap. So, like this sigma q q cap means sigma q square cap. Correct? So, if I take one value here which is s for the kth dependent variable, if we take a value here s k square, then this corresponding the population case, that is sigma k square, but we are estimating this one. Getting me? Then what is the relationship? Relationship is s k square equal to n minus p minus 1 sigma caps k square. So ultimately when you are saying k, that means we are talking about yk, variable yk. You are going back to your multiple regression case. Okay. Now what you require now? So you know what are the things you know? You know the things what is given to you now, that beta cap point estimate, this is my point estimate, it is known, and I know that this also followed that normal distribution. What type, what normal, multiple or multivariate? Beta cap is, what is this beta cap? N cross p plus 1 cross q, multivariate case. Now what happened? I am writing here beta k, then we are going back to this MLR case, so that means this will be 1. So then this will become p plus 1. Now p plus 1, then this beta k into x transpose x inverse sigma k square. Correct. The sigma k square will be estimated. Sigma k square will be estimated, and ultimately what will happen then? That sigma k square you will be replacing by like this. Sigma k square is s k square by n minus p minus 1, where s k square is the kth element of the SSCP matrix. Kth element of the SSCP matrix. Now question comes that what will be the confidence region? Confidence region, because when we are coming to the multivariate domain, first is confidence region, then what will be the confidence region of what? Confidence region of beta k. Here we are going back to individual variable beta k, that we have seen in MLR. What will be the simultaneous confidence interval of beta kj? See, that j stands for number of j equal to 1 to p, 0 to p, 0 to p, j equal to 0 to all the regression coefficients related to x variables. K stands from 1 to q. Then comes that what these two, and then comes that what will be the confidence interval of beta kj. Okay. Now if you recall in MLR that okay, we have not gone for this confidence region because of the robustness of regression, and also we have described what is this, and also we have described what will be the simultaneous confidence interval of beta kj using Bonferroni approach. We have used Bonferroni approach. So, but what we have discussed there mostly beta j case, there k was, that one variable k was not there. So, in MLR we have discussed about beta j with respect to the estimate of this, and you have seen that we says that beta j cap minus expected value of beta j cap divided by standard error of beta j cap follows t distribution that we have described. So, the same thing prevail here also. Same thing we can use here. we can write that beta kj minus expected value of beta kj divided by standard error of beta kj, all cap, these are estimate one. This follows t distribution with n minus p minus 1 degree of freedom. See, here also the degree of freedom is n minus p minus 1. Earlier also we have seen this, the n minus p minus 1 in MLR case also, because the x side remains same in MLR as well as this case. Okay. So, then I think this does not require discussed here, because if you follow the my earlier lecture of MLR, then you will be able to find out that the same thing is given. So, what I mean to say, suppose this one is minus t n minus p minus 1 into alpha by 2 and this one is n minus p minus 1 alpha by 2. So, this side is alpha by 2 and this side is alpha by 2, and then this is your 100 into 1 minus alpha percent confidence interval for what? For beta j. What is this beta j? Beta j is basically expected value of beta j. Here we are using beta kj, because k is coming from the dependent side, expected of value of this. So, you can write then, you can write that t n minus p minus 1 minus alpha by 2 less than, if I use less than equal to less than, let us write less than, then this will be beta kj minus beta kj cap minus beta kj by what is the standard error of beta kj? X transpose x inverse sigma k square we found out. Sigma k square is nothing but AC square by n minus p minus 1. So, you can write down, I think I have given in somewhere here, that x transpose x inverse then your sigma k cap square, which will become AC square by n minus p minus 1, correct. So, that value will come here, that value will be coming here. So, I will not writing this. So, straightway I am writing AC this, because of you can beta kj less than equal to t n minus p minus 1 alpha by 2. So, ultimately what will happen, your confidence interval will become beta kj minus t n minus p minus 1 SE beta kj less than beta kj less than beta kj cap plus t n minus p minus 1, definitely alpha by 2 is there, alpha by 2 into standard error of beta k j cap. So, how do you know beta k j cap? The standard errors, I told you x transpose x inverse sigma k cap square, which will give you x transpose x inverse s k square by n minus p minus 1. Okay, you check this one. If there is mistake, you report to me. I don't think there is mistake. So, ultimately this is your this one is your 100 into 1 minus alpha percent confidence interval. So, this one let us see the result. I have, if you go back, so let us go to the data set initially we have considered. So, this is the data set, this one profit, this is your sales volume, this one is the constant term for x0, this is absenteeism, this one is breakdown hours, this is M ratio. So, that means 1, 2, 3 variables from the independent side we have considered and 2 variables from the dependent side we have considered. Then what I have used? I have used SPSS, then SPSS result is this. Getting me? Now see the profit intercept 10.897 and its standard error, that x transpose x inverse, that CJJ, that same formulation if you use, the standard error is 2.572 and what will be the t value? T value is basically under null hypothesis is true, that means H0 beta Kj equal to 0, then your beta, the estimate by the standard error. So, 10.89 divided by 2.5, how much it is coming? If I multiply this into 4, I think this is coming exactly. So, see, so intercept 4.237, t value is 4.237 means it is quite large value and the probability significance level is 0.003. So, similarly absenteeism breakdown M ratio, and you see ultimately what is happening here, that absenteeism is not significant, breakdown is significant, but it is slightly higher than the 5% significance level, but still it is to be considered. M ratio is very significant from profit point of view. If you go by that sales point of view, suddenly even breakdown hours are also not coming into that significant case. Okay. So, that means what I mean to say here, I mean to say here that you know beta, these are the coefficients. So, this side is beta 1, this is beta 2, this is the standard error part, then this is also standard error for this. Now, once you know this beta as well as its standard error, so also you are in a position to find out the confidence interval. That instead of confidence interval, here it is given the significance level as if H0 is framed that beta equal to true. But it is also possible to find out that this one, the confidence interval, you see this figure, that lower 95% confidence interval, lower bound and upper bound, this is given. And if you see that SSCP matrix, here it is given, you see SSCP matrix, that what I said, that SSCP matrix. So, this is the first for the profit, that is the SSCP that value, and this one is your sales, the diagonal elements. Okay, these are the S square, S1 square and S2 square, these values are there, and you know that n minus p minus 1, that value is known to you, and you will be able to find out the variance standard error part once you multiply it by x transpose x inverse. Okay, just you check, because what I mean to say, I have not checked this by hands on calculation, I have not checked, that you just check for one, that SSCP matrix, EP matrix is available, and your x transpose x is also available, that inverse is available, and you know that n, p, everything is given, that I ask you to check the what are the confidence bound you are getting, that interval part that you check, and I think you will get the same. It has to be, if I am not committing mistake in the theory. And for this part particularly, this sampling distribution of beta, that estimation as well as sampling distribution of beta, it is almost similar to multiple linear regression. So, you I think you do not face any problem here. Okay. Your problem will be in model adequacy test, which we will discuss next. Okay. In detail we will discuss this model adequacy test in the next class. Thank you.